Can go right now.
All right.
I see you click the record button.
Yeah.
I don't know where that will go, but it will definitely record it. So yeah, Damien, just for housekeeping, I transfer the host to you. That way, if anyone raises their hand or has questions, you can look at that while I'm presenting, because I won't be able to manage that and present.
Sure. Understood.
So appreciate that. Now let me share my screen here. Y'all should see a nice, humorous cover slide. Everyone see that? Okay.
Yes, I can see it fine.
Cool. Excellent. Okay, so this is a little talk I put together called Understanding Probabilistic Data Structures with 112,092 UFO Sightings. Just out of curiosity, does anyone know what a probabilistic data structure is?
I think, isn't quicksort a probabilistic algorithm? Or
that's probably true.
Bloom filters.
Bloom filters, ding. That's the most common one everyone knows. Do you know how a bloom filter works? Anyone?
it tells you whether or not something's definitely not in a set. And I don't remember. It's a way. It's similar to hash tables, isn't it?
Yeah, we're going to dive into it in detail. So if you don't know, you'll know by the time we're done. So I'm going to talk about 3 of them, and I'll get into it. But that's the main theme today. Is we're going to talk about things like bloom filters. I'm Guy Royse. I'm a developer advocate at Redis Labs. You can follow me on Twitter. And on GitHub, you can actually, out on GitHub is code to go along with this talk. I've got some examples of doing several probabilistic data structures. Most of my samples are in JavaScript. None of them are, unfortunately, in Python. Unfortunately, none of them are in Python. That would be a better way to say that. But it's on my list to port them over there as well. But you can look at them and see how they function as code. And if you want to go read my outdated blog, you can go to guy.dev. And see that I blog yearly at least. So 112,092 is an oddly specific number. But as it turns out, that is the number of UFO sightings that I have from a data set that I got off of data.world. These are UFO sightings gathered by the National UFO Research Center, the NUFORC, which I think just covers the United States. And so that's a lot of records. Some of you have may seen my Bigfoot talks where I have like about 4,500 Bigfoot sightings. There's a lot more UFO sightings than Bigfoot sightings. And the data is actually kind of interesting. You've got a summary of the the sighting. 3 saucer-shaped ships, high in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. That's the summary. You got the city and state, Salem, Oregon. You got a date time. This one happened on September the 15th in 1950 at about 2 o'clock in the afternoon. They cataloged the shape of the UFOs, how long the sighting lasted. There's a link here that you can go to on the NUFORC site to read the full report. There's the text of the report, which I have abbreviated to fit on screen here. And then we've got the city's latitude and longitude, which are just derived from the city and state. That was created by the person who gathered the data set. And this person, he actually went out and screen scraped the NUFORC site to generate this data set, to share it with us for our important research. And so we're going to use this data as sample data in all of our exercises. And I have a demo that uses Redis Bloom, which is a module that extends Redis to find the top 10 most commonly used words in UFO sightings. And I use this data set. It also determines the top 10 most common shapes. So a fun little exercise. That is in Python. I asked earlier, what's a probabilistic data structure? I actually went on Twitter when I was putting together this talk because I wanted to come up with a clever name. And like I was going to call it improbabilistic data structures or something like that, to sort of, work with that UFO theme. And I said, so, have you heard of probabilistic data structures? almost 60% had never even heard of them. About 20% had heard the term, although I suspect they may have heard the term right up here.
Mhm.
And because we sometimes are literal-minded bastards like that. 10% knew what they were, and only 10% had ever used them. So I'm like, well, I can't not have the name probabilistic structures in my title name. But it also told me that most people have no idea. Only 1 out of 5 developers either knew what they were or had used them. And that's like Trident dentist ratio numbers, right? That means there's a lot of education to be had. So I thought, well, this is actually a valuable talk to have. In order to understand probabilistic data structures, I thought it might be useful to talk about deterministic data structures. And if you've got a computer science degree, which I don't, by the way, and many people do, many don't. Some of these will be familiar to you, and even if you don't, you'll recognize them, right? You got like lists. A lot of languages have a list. Arrays, graphs, trees, tables, like a hash table or a dictionary. Python has these. We don't normally have to build these data structures ourselves because we're using higher level languages. But if you started some of your programming back in C and C++ like I did, I remember back in the early 90s, these data structures weren't free. You actually had to write linked lists yourself. And Jim's laughing because he's had to do this as well. And in a way, they're kind of fun, but they're deterministic, right? The deterministic data structure means I put a thing in it and I get the thing out of it. It works exactly like I think it would. There's no wiggle room. There's no weirdness. It's deterministic. You do a thing, the thing happens. And I'm going to look specifically at hash tables because hash tables make use of hashing algorithms, hashing functions to store things in an interesting way. And that same principle that's being used in hash tables is used in a lot of these probabilistic data structures. So a hash table is a simple key value pair store. You put in the city, state, date, time, shape, summary. Here's our UFO data. Key value pair. We've used this a million times. If you're using a dictionary in Python, you're using a hash table under the covers. There's someone that probably says that I'm wrong on that. I haven't actually looked to see that it's implemented specifically as a hash table, but my money's on it's a hash table. If not, there's something similar to it. But it's just storing it. You give it a key, you get the value out. You give it, you set a key with a value, it puts the value in. And they do this internally using hashing functions. And if you haven't used a hashing function before, you hand it data, you hand it a numeric seed, and these functions will then turn that into a hash. In essence, they'll take big data and flatten it out to a fixed size bit of data, maybe a 64-bit number or a 32-bit number. And so you can take like a big document, a bunch of bytes, and cram it down into a single hashed value. There are a couple types of hashing functions. Well, there's two I'm going to talk about. When I'm talking about hashing functions, the kinds we use in these sorts of talks or in these sorts of data structures, we're talking about more simpler ones. There's cryptographic hashing functions like SHA and MD5, which isn't as secure as everyone thought it was at the time. Those are specifically made so that you can't reverse engineer them. They're made to be more robust, more secure. The types of hashing functions you'd use for data structures, you'd want them to be faster than that. Those cryptographic ones tend to be slow. So you want a faster hashing function like a murmur hash or an FNV. And so you hand those things a seed number, you hand that some data, it spits out, say, a 32-bit or 64-bit number, or maybe a 16-bit number. And then when you go to use a hash table, what you're doing is you've got an array that you've predefined. You can see it right here. And here we have a comically small one with 10 elements. And can you guys see my mouse cursor, by the way?
I can see your cursor fine.
Good, good. And so you put the key city, because we want to add the city of Salem to our hash table. We run it through our hashing function, and that's going to generate a 32-bit number. But we only have 10 places to put it, so we'll do a modulus of 10 and get an index for the array. And then you shove Salem into that column, or into that bucket. And when you go to retrieve it, you just hash it again and go find the thing at that location. Here we're adding Oregon as well. States hashes out to be index number 4. But sometimes, while the hash itself probably won't collide because it's a really big number, when you modulus them, you've got a smaller space, and so collisions are inevitable. And so what you do is you use a linked list to store multiple items in the bucket. And so you hash shape, you get a key, you go and say, oh, there's 2 things in the bucket, walk the list until you find the match that matches for the hash of your key. Yes,
Guy,
sir.
do you ever do the other method where you just remodulus, where you put it into another slot instead?
There's another technique where you can put it in the next line down. It's just another way of chaining them. So you do the modules, it takes you here, but the hash doesn't match, and so you go down to the next one and the next one. There's other techniques. This is the most basic.
Yeah.
There's actually whole documents written on this, and I don't really know all the techniques, but this is the core idea of how a hash table works.
All right. Thanks.
My phone's ringing. I'm like, is it my doctor? I hope not. So it looks like it's Westerville Schools, actually. So then you can add several things, and your hash table can be quite full. Here we've added Salem for the city, the shape is disk, state is Oregon, timestamp, and the text. And so when we go to read from it, we hash city, and it gives us a number, and that was going to return Salem. If we had hashed and said shape, we would get Salem here and say, no, that hash doesn't match, so we'll go to disk. And so we walk down the chain. And actually, I live streamed last Saturday a session where Brendan Enric and I went through and coded up a hash table in JavaScript. So if you want to see that working and see us coding one up, you can go check that out. I've got a Git repo for that. Actually, let me share that for you, if you don't mind the JavaScript. It's called data structures. Here we go. I'm going to go ahead and paste that in the chat. How do I get to the chat when I'm full screen here? Is it here? As I fiddle with things. It's exciting talk watching Guy fiddle with things, isn't it?
That's why I'm here.
Yeah, that's right. Let's just watch Guy fiddle. Fiddle while Rome burns, right? So yeah, so when you have this collision, you go through and you just walk the list until you find the one that matches. And when you're choosing data structures, there's really 2 things that you're looking at, right? You're looking at time complexity and you're looking at space complexity. Time and space. It's like aliens and UFOs, right? The time complexity in the terms of how fast is it for me to do certain operations against this data set versus how much space does it take, right? So hash tables tend to be sparsely populated a little bit. There's gaps in them. And so they consume more space, but they're fast to access because you're hashing and you're doing direct array access. Accessing any item in the hash is just as fast as accessing any other item in the hash, assuming you don't have to walk down the linked list. Whereas if you have a linked list, walking through that's expensive, but modifying it's actually a very cheap operation. Arrays are fixed in space. They are a constrained size, but they're very fast to access. And so you're always trading off against time and space, or sometimes different types of access and time versus other types of access. Because it's not really time versus space. It's just there's time complexity and there's space complexity. The time complexity is certain operations are fast and others are slow, but if you have a different structure, different ones are fast and other ones are slow. And you're choosing your data structures based on what your needs are and the type of data you're going to put into them. But there's actually a third thing that we can look at to change how we interact with these data structures. We can create accuracy complexity. So in addition to making things faster or slower or to consume more or less memory, we can also say, how much error is acceptable? if I could greatly reduce the amount of space things take and make it really fast, would that be worth a 1% error rate so that when I shove data into it, I don't always get it out, but I get it out often enough? Is that acceptable? And so that's a whole nother level, layer of complexity. And this is what probabilistic data structures are. They're bringing that complexity, that accuracy complexity to play. Here's a simple example of a absolutely terrible probabilistic data structure. I don't think anyone's ever done this. I don't recommend it. But you don't have to actually do chaining in a hash table. You could just, shove the value of city in and say Salem, then shove the value of shape in, and it overwrites the city with disk. And then when you go to retrieve city, it returns the wrong value. And so sometimes it's lying to you. You've got an error rate. This is technically a probabilistic data structure. I don't think anyone should ever do this. I think it's a terrible idea, but it's showing how you can build a structure that's very similar to a hash table that it has error, but it's not always erroring. So it has a degree of error.
Guy, do you when they teach hash tables, there's some function that lets you know how many expected misses you're going to get when you have a hash table like this? If you calculate that, you can find out what your expected hits are going to be.
Yeah, you could you could do that. However, I just would recommend not using this kind of structure because it's just something I made up to show how a probabilistic data structure could work. So it's just it's just an example to show how a data structure could use hashes and lie to you sometimes. And the advantage of this would be that it's faster, but the disadvantage would be that sometimes you don't get the city anymore and you lose the data.
Okay.
I like to think that probabilistic data structures are kind of like JPEGs. Anyone get the Devil's Tower joke there, by the way? Close encounters of the third kind. This JPEG means something. But a JPEG is a little bit lossy, but good enough. This is the trade-off you're making. This pixel up here that I'm allegedly pointing to, right there, may not be the exact shade of blue that we think it should be. It could be more closely resembling its neighbors, because a JPEG is a lossy compression, but you can't tell, and so it's good enough. And so it's like, well, this isn't pixel perfect, but is acceptable. It solves the problem and saves us space. And so that's the same kind of trade-off. I'm going to do an incomplete tour of probabilistic data structures. A couple here. We've got Bloom filters, cuckoo filters. They are like sets. So they let you calculate, they determine membership in different ways. If there's a little red dagger there, that means that's included with Redis Bloom. If there's a little double dagger, that means it's included with just stock Redis. So Bloom filters and cuckoo filters allow you to check membership. You've got hyperlog log, which lets you only allows you to get the cardinality of a set, the number of items in it, but doesn't let you check membership or get back the values that are in it. You've got count sketch and count min sketch. And we're going to get into one of those. We're going to get into, we're not going to get into either one of these in these talks, but they let you count frequency. And so that's a little different than cardinality because you're counting the number of how frequent items are in the set. You've got ranking, and which is similar to frequency in the sense that ranking puts things in an order, and the order is the priority. Whereas frequency is you want to understand the sort of histographical relationship between the items in the set. And then you've got things to determine similarity like min hash and sim hash. We're going to go into detail on Bloom filters, headkeeper for top K, and min hash. But I'm going to do the obligatory Redis plug here and say that Redis Bloom, which I mentioned in the previous slide here, is a module that extends Redis. So you've probably used Redis in your career. If you haven't, you should use it. It's a really cool in-memory key value store that you can use as a cache, as a database. But it's got a lot of extensions where you can extend it. And I've got a few icons for ones here. The key one here is Redis Bloom. And Redis Bloom, which I think is this logo here, adds probabilistic data structures that are useful, like Bloom filters and cuckoo filters and top K. There's other ones. We got like graph database offering, which I've been playing with quite a bit. You got some AI stuff to host TensorFlow models. You got some time series search. There's a JSON module that allows you to parse JSON in Redis, which is really nice. And Redis Gears is probably the one that Python developers would care the most about because it lets you run Python on the Redis server. So there's a Python runtime in there. I have not played with it, so I don't know exactly how it works. It's on my to-do list. Lot to learn. So, but check out Redis modules. They're actually pretty cool. And Redis Bloom is one of them. And two of the probabilistic data structures are available in Redis with Redis Bloom. So I kind of talked about this already. Membership is something you do. Is this thing in the set or not? Right. That's the thing you can do. It gets a set. Test for membership. Cardinality. How many things are in a set? How many unique things? That's just counting. I mean, cardinality is a fancy word for counting. We're just counting the things in the set. Frequency shows how things in the set relate to each other. Like I said, sort of a histogram. Rank shows relative order in a set. This one is got more than the other, but the count doesn't necessarily matter. And similarity is this thing like the other. And by the way, this is my favorite picture in all of the pictures that I put in my slide deck here. Just, it's kind of, I don't know what to say about it other than it's very similar. So similarity you could use to determine like, hey, is this term paper like this term paper over here? That might be useful to know. Those sorts of things. So Bloom filters. A Bloom filter is measurement or membership. It determines membership. You can add things to a Bloom filter. You cannot remove things from a Bloom filter. You cannot count things in a Bloom filter, but you can say, you can add things and say, is this thing in the Bloom filter or not? And the Bloom filter can respond with no, it is definitely not in the set, or it can say, probably it's in the set. It cannot say, yes, definitely it is in the set. Their big advantage is that they are fixed size when you create them. You create it and say, it's this size, it's fixed, it doesn't get any bigger, and they're fast. However, if you create them for a particular number of items and you keep adding things beyond it, it gets inaccurate very fast. And so that fixed size, you want to determine that carefully up front. Bloom filter's got three main parts. You've got your hash functions and seeds. And so you've got the same hash function. So this is like a murmur hash, and you've got n number of seeds that you're going to use to run through with those that hash function. And it's got a bit array of fixed width. And so this, the things that you can use to determine the size of the Bloom filter is how wide that bit array is and how many hash functions with seeds that you have. And so if you have more hash functions or a wider array, you can store more stuff. But then the more hash functions you have, that has a performance hit because it slows it down because you've got to calculate that hash each time. It works by running a string or whatever data you want to put into the Bloom filter through the hashing functions. Here we've got a Megatron in the bushes. This is a actual UFO sighting from the data set. It's a delight to read. Whenever a UFO sighting has a Transformers reference, I'm there. So, and so you take this string, you run it through the hashes, and you get 4 or 3 in this case. I picked 3 because it fits on the screen. 3 fingerprints, 3 hash results. I also picked 16-bit numbers just because they were shorter and easier to work with. And so we get 3 unique numbers, and we modulus them with 10. In this case, we're using 10 because our Bloom filter is 10 entries wide. And again, that's so that it would fit on the screen. A real one would be bigger than this. And those give you indexes, 5, 0, and 6. And you take those indexes, and much like a hash table where you put the value, this time you just put a 1 And so 5, 0, and 6 all have their bits set high. So these hash functions lead to indexes. We set them all to true. To read, we pass in that same string. And I say read, but we're not really reading, we're checking membership. It runs through the same hash functions, gets the same numbers, and we just go read the bit state of those 3 indexes. And if they're all true, then it's probably in the Bloom filter. I keep saying probably, and you may not see the probably yet. But let's add another one here. I seen a UFO when I was about 13 years old. That one actually happened here in Columbus, Ohio, if you look in the data. I'm proud to be a Columbusite. So you run that through, you get a different set of numbers, but you'll notice that this time one of them collided. 6 was in both of these sets. But that's okay, right? If we go back and read the previous value, they'll all be true. If we go and check this value, they'll all be true. There's just an overlap. And this is actually why you have multiple hash functions, multiple seeds, is so that when you do get a collision, it doesn't return a false positive as often. You're probably starting to see where the false positives come out, where the probably comes in, because you can add something that has a complete collision. So investigators from the Bigfoot Field Researchers Organization observed a glowing green-blue sphere. It generates 0, 1, and 16. All of those are already set high. They're all set to true. And so there's nothing to do here. And if you go and read it, it's going to say that was added. But if you hadn't added it, you just went and read it, it still would have said this is true, even though it was never added. And so you can't know whether a thing's been added for sure or not, because other things could have created that same bit pattern, and the collisions of various adds could have created that same bit pattern to make that true. However, if you ever get a 0, you know that this has definitely not been through there, because nothing sets anything to 0. 0 is the default background. And so this is why Bloom filters can say definitely yes, definitely not in there, probably in there. And you can control that by varying, I mentioned earlier, the number of hashes and the width. And here is the formula to do it. Very easy, no problem whatsoever. This actually isn't as intimidating as it looks, because you can take the number of bits, you can take the number of items and the number of bits and solve for K in this formula down here. And then plug those values into here and find out what your false positivity rate is. And if that's acceptable, then you're good. And if it's unacceptable, then modify the number of bits until you get something that is acceptable. And so this is a way that you can compute how wide you need to make these things. There's also an online tool to do it, and that's a great way to do it as well. Is just go on there and calculate that. But of course, the best way in the world to do it is just to use Redis. So Redis has a Bloom filter built in. If you call bf.reserve, when it's not built in, it's part of the Redis Bloom. But if you use Redis Bloom, you have a Bloom filter.reserve. You can give it a key name that you want, the error rate that you find acceptable. So this is going to be 0.5%. And a capacity, how wide do you think this thing needs to be? How many items do you want to store in it? And then it will create one for you that can handle that capacity. And then to use it, you just call add. So bf add UFO shapes disk, bf add UFO shapes light. And there's also a multi-add. So you can do a light and teardrop. So you can add multiple things at once. I actually think add should have just taken multiple things, but this is still okay. And so you can add things to it. And when you go to check, you call bf exists. And it will say 1 for probably and 0 for no. And you can just use them. And so that's a Bloom filter. Any questions so far?
Yeah, about the width on it. You never need to exceed the variance of your data for the width, meaning that if you probability rate is lower than the number of possibilities you could have, then it's the same as 0.
Well,
Like,
yeah, say that again. Yeah.
if you know how many, let's say you have something with the whatever 64,000 different combinations. If your probability rate's lower than that, it's the same as 0. So at least you know the upper bound of how much memory a hash table could take up.
Well, I'd say probably. And because there's no guarantee. I mean, you can define that upper bound. If you start getting into that territory, though, you might as well just go ahead and use a regular set, because you can crank these values up so high that the odds of having a collision are, heat death of the universe sorts of numbers. But if you do that, then there's no point in using a probabilistic data structure. Because then they're taking up more space than if you had just used an array and just walk through it, or a list or something like that. But yeah, you can get an idea of the upper bound of memory that you would probably need. The key thing here is the amount of memory that gets allocated when you create it is fixed, and so they don't grow, because the memory that you have is just this bit array here, and that's all the memory you have. And so if you've got 65,000 bits, then it's what 8K. So they can be very nice, small and tight. So that's the big advantage you're getting.
Okay.
I hope that answered your question.
Yeah, it does.
Cool. Okay, let's look at minhash. Minhash is not part of Redis, but it's really fascinating. And what minhash does is it determines the set similarity between documents. And set similarity is this idea. It's called a Jacquard similarity. So here we have Scalder and Molly, who have been face swapped so that they can be part of a synth pop band. And here are the states that they've seen UFOs in. So Scalder has seen them in California, Nevada, Oregon, and Wyoming, New Mexico, and Ohio. New Mexico and Ohio, we get what Area 51 and Hangar 18. That checks out. It's Roswell in New Mexico. Nevada, Area 51's in Nevada. Molly has seen them in Florida, Kansas, South Carolina, West by God, Virginia, New Mexico, and Ohio. And so Jacquard similarity is simply the cardinality, the count of the union of these sets, and the cardinality of the intersection. You take the intersection divided by the union, and that gives you a similarity. And so these sets are 20% similar, because 2 divided by 10. It's actually a really easy concept. Calculate that similarity. However, if you were to just take like 2 documents and count all the words and then do this, that wouldn't work very well at all, because we're all using the same words, right? And so what you do is you can turn a document into a set. And you do that using a process called shingling. And shingling is you extract out a trigram, 3 words next to each other. And then you extract out the next trigram and the next trigram. And then you go all the way through all of them. And so this little sentence here creates these shingles. And so now you've turned the document into a series of groupings of words. And collision between those is less likely. And then you can do the same thing with these words. You can take this document and compare the shingles as sets. And so here is Scalder's reports, and here's Molly's reports. And we're trying to see whether they've copied their reports back to the FBI. Who was their boss in the X-Files? I can't remember. I wish I could remember his name. That'd be great. I need to put his picture on here. But you can compare these 2 sets and do the same calculation and determine that their reports are 0.636% or 63.6% in agreement with each other. It looks like copied some stuff from each other, but not everything. And so you can do this to compare documents. But it's excruciatingly slow to do that with a lot of documents. And so what you can do is you can calculate a min hash instead. And so with min hash, you have a series of hash functions again, and you hash every single shingle in the document. And you run this through each hashing function, and you get a list of hash values. I'm using nice small ones here so they'll fit, but these should be like 64 or 32-bit numbers. And then you take, for each hashing function, you take the minimum one and save it. And now you have a list of minimum hashes for that set of shingles. Excuse me. So all these shingles go through here, create a bunch of numbers, take the smallest. Goes through here, take the smallest, goes through here, take the smallest, giving us a set of numbers. And so we do that for Scalder. We do that for Molly. And we end up with a set of numbers equal to the number of hash functions that we chose to use. And then we can calculate the Jacquard similarity using those numbers instead, which is a much smaller set and is just a straight up numeric comparison. And so here we only use 3 hashing functions, and we find out that these 2 reports, which are the same data, have a Jacquard similarity of 50%. And that's because we don't have as much resolution. We only have, 2 sets of 3. And so, there's only so many combinations there. If we increase the number of hashing functions, we would have got more numbers, and then we could get more granularity out of this similarity. But this, you can use this to compare documents on the web for web crawling and say, this document is 80% similar. I'm not going to re-index it. And you can treat that as like a threshold. And you can build up these signatures of documents that are faster and smaller to work with than working with the entire document. So once you've calculated all the minimum hashes, the min hash of a document, you can just hang on to the hash itself. And so this allows you to compare them. I showed here 0.636 versus 0.5. That's just a result of how many hashing functions we had. We could have gotten it more accurate. It's also true that all the numbers on my slides are completely made up, so that's a factor too. Questions on min hash? That one's a little more complicated.
Do you know anyone using it in production?
Google used it for a while, but I think they switched to SimHash. They were using it as part of their web crawling. I don't know anyone personally. I know companies do.
There's a cool algorithm based on min-hash used in bioinformatics called MASH for comparing genomes to each other.
Oh, cool. Yeah, I was using documents here, but they wouldn't have to be documents. I mean, you wouldn't have to use hashing words. You could shingle other types of data. Shingling actually kind of reminds me of the way that convolutional neural networks work, where you have the filter that slides along the image, because you're going 1 pixel over each time, and here you're going 1 word over. And I can't help but wonder if there might be tricks you could do with that for like image recognition and stuff like that. Maybe as like a shortcut. Like that might be an easier way to do optical character recognition than using something like actual convolutional neural networks.
Well, there's word vectors you can use to get, if you want to do understanding of document content. You can you could combine that with this and translate a document from the words to the word vectors, and then run it again in another pass to find out similarity of definition, or of similarity of vocabulary.
Oh yeah, that makes sense.
Because imagine you have a synonym for a word, and it's used in 2 different ways in 5 different documents. you could find out which documents are similar by usage of the word and not by just the presence of the word.
So you get sort of like a fingerprint on that document.
You would get accurate to meaning more than to, contain just the word being typed in there.
Yeah.
But
It'd be interesting to map the lexical space to a semantic space and then do the same comparison, because then you could see if someone just went through a term paper and changed all the and took a term paper and a thesaurus, right?
eh,
So that's min hash, and so I think it's kind of neat. And then we've got top K, which is actually heavy keeper. Top K is a problem to be solved. Heavy keeper is an algorithm that does that. And so what top K does is it ranks items, puts them in order, but it only keeps track of the top K items. So if you want to get, you've got a bunch of data and you want to get the top 10 most commonly used words in a UFO sighting, you could use heavy keeper to do that. And actually specifically it uses heavy keeper and min heap. And heavy keeper is an algorithm I'm going to go into. Min heap is a heap. I'm not going to go into how heaps work. Suffice to say is the small thing's always on the top, and that takes did I get that backwards? No, I had it right. The small thing is always on the top, and you just keep all the big things. With heavy keeper, you if the thing you need to add to the heap is smaller than the thing at the root, then you don't add it. That's what it's doing. And I don't honestly understand very well how heaps work because, like I said, I don't have a computer science degree and I just didn't dive into that detail. But I know you can use them for sorting and stuff like that. And that's what's, in essence, top K is doing. It's not really the interesting part of top K. Heavy keeper, and I haven't looked at this in a few months, and so bear with me here, has, again, a series of hashing functions with different seeds. And then you've got these arrays where you've got an index. And so you're doing the same hashing thing where you're taking your data, running through a hash, you're getting an index, and you're putting things in that index. But the buckets consist of a hash value and a count. And so when you get a brand new heavy keeper, everything's null and all the counts are 0. And so here we've got just three arrays here, and then I'm just showing them as being n wide. When you go to add a value to heavy keeper, like say the UFO shape of object, that's one of the popular ones. I saw an object in the sky. What was it? It was an object. It's object-oriented UFO sightings. You hash that value. You get a hash value out of it. You modulus that with the width of all the arrays, just each array. They're all the same width. And you get an index, just like before. We've seen this pattern a couple times now. And then we take the hash value itself and put it here in the hash part of the bucket, and we change the counter to 1. Or we increment the counter by 1. So we've added the value here. We get 212 back. So in position 2, we add this hash. Down here, we add the same thing over here, and we add the same thing over here. So you probably are understanding what's happening, but not why yet. The why here is a little hard to get your head around, but this is called heavy keeper because it hangs onto the heavy stuff and throws out the small stuff. If we add the same value again, we'll go out and say, hey, these buckets are here, so we'll just increment them. Now they all have a value of 2, so they're getting heavier. If we go to query the count, we'll go out and we'll hash it, pull the values back, and we'll say, is the hash number match? Yes, yes, yes. Take the largest out of all of them. So in this case, it doesn't really matter. They're all 2. It's going to come back and say, object is in the list 2 times. Or in the set 2 times. If we add another value, here we've got a hash function of 605, we got the value of light, and we're getting different values here. And so here we don't have a collision on our index, and here we don't have a collision on our index, but here we do. Something's in that spot already. And so that's problematic. And so what we do is we follow this little function here. Is you might think, well, then we'll just drop it down by 1, right? Well, the answer is that's close. We might drop it down by 1. And so we've got this probability of decay, the chance that that number will drop, and is equal to b to the power of negative c, where b is the rate of decay, which is a number that's greater than 1, but about 1. So like 1.01 or 1.005. And so b to the power of negative 1.05. Well, here the example, we've got 1.05 to the power of negative 1. Sorry, I got this backwards. 1.05 to the power of negative 2 in our case, the count, that's how many items are in here. We got 2 items right here. And so we take how many items are there currently, and we take our preset number, our 1.05 or whatever we want that to be. We do this math and calculate a 0.907% chance of decay. Now, as the count gets bigger, this number is going to get closer and closer to 1, or making it less and less likely that will decay. This number is going to get smaller and smaller. Yeah, it's going to get smaller and smaller. The key thing here, I'm flipping the math in my head because I'm dumb, but the key thing here is this number increases, and that it makes it less likely that the item that's in there will be decremented. So if this was like there were 1,000 items in this position, then it'd be 1.05 to the power of negative 1,000. And that makes it way less likely that when we generate a random number, that it's going to decrease it. And that's all it does, is it decreases it. And so if the probability of decay happens, then it decays by 1. And this is why it's called a heavy keeper. It hangs onto those heavy things. And so we call these mouse flows and elephant flows. So the elephant flows are the data streaming in, and we're seeing a number a lot. And so there's a lot of it. It's heavy. It's an elephant. And so those numbers get really high. And occasionally mice will come in, and they will land in that same spot, but maybe they knock the elephant down a little bit, but not significantly. Occasionally mice come in, they can go. They go there. If you get enough of the mice over time, then those numbers will start getting increasing, and it'll whittle it down over time. But it sort of favors things heavy that come in first. And so in this case, we're going to say that decay occurs because it was fairly likely. And so we reduce this count by 1. So light is stored here and here and here, I think. And it's not stored in this array at all, but it whittled away at another one. Now, if we query light after that decay, we only get matches here where there's green. There is no match down here. And we look and see it's a 1, and its count is accurate. If we query object, we get all 3 of these, but this number is now lower than it was. But we take the max. And so having multiple arrays preserves our count. So even though some of them shrink, not all of them shrink. And so that preserves that. And the reality of it is that all of them can shrink. And so the counts coming out of a heavy keeper are unreliable. They're guaranteed not be bigger than the correct number, but it's fairly likely that they'll be smaller than the correct number. And so what happens here is that when we're adding things, we got new counts, we update our min heap every single time that happens. And if it's appropriate to push that onto the heap or not, we do. And so that heap just keeps track of the top K items that we have, however big that heap's supposed to be. I've made this one a size of 5. And so you use this heavy keeper and the heap together, and the heavy keeper is keeping track of the things that are big and keeping track of the counts. The counts aren't very accurate, but they're accurate enough to get the ordering correct. and then the heap keeps track of the top items, and everything else gets thrown away. The heap doesn't keep track of that. Now, this is very easy to use inside of Redis. You call topk.reserve. You give it the shape or the key name you want, and you say, I want this many items in my top K. I want the top 3. I want to have a width of 100 buckets. I want to have 5 hashes, a depth of 5, and I want my decay to be 0.9. And so Redis has inverted it. So instead of 1.05, you take 1 over 1.05, and that would give you that value there. And that will set up a top K structure for you in Redis. To use it, you just add items using top K add, and it adds them. There's not much to be said about it other than it adds them. And then when you go to query it, you can say query disk, and it will say, yes, it's there. You can count it, and it will give you the count out of the heavy keeper, which could be lower than reality. And if you ask for the list, it'll give you the top 3 items, because we said it was up to be 3. And so you can use topk.list. So it kind of does it all for you if you want to use this feature in your application. And that's pretty much the talk. I've got a demo here if y'all want to see it. Want to see this in action? Okay. Let me get this up here. Yes, my computer's called Big MacBook. Talks, probabilistic data structures, code, demo. Okay, what's different? Oh. Why do I have a Gradle file in here? Good God. But by the way, my monitor that I'm projecting from is up here. This is why I'm looking away from everyone now. It's dot slash source.
Because I can't speak to that. Like I said, you're going to have to ask him.
Okay, that gets my proper Python version going. And I've got 2, let's see if I'm going to bring up another terminal into here. Go to the same directory. It helps if I put a CD in front of it. There we go. Source, just copy this here. So I've got Python there. So I've got 2 Python files here. Get this up here. Can you guys see my code? Is it big enough? That's probably a better question.
Usually, when you have this much text on a screen,
yeah,
it's hard to read. But we're all looking at this on on normal computer screens at normal height. This is fine.
It's kind of nice, isn't it? So app.py is a little Flask app. And all it's doing is it's got 2 routes for shapes and words. And all it does is talk to Redis and queries the UFO shapes and UFO words, top K values. Then I've got some stuff here to serve up generic files.
Well, thanks for showing some Python to us.
Yeah, I thought I should. So here I can go Python app.py, but that won't work yet because I probably should launch Redis. That might help. Do I have a? Oh yeah, I can do Redis from here. So Redis server Redis conf. There we go. Now my Redis is poorly configured, and so it takes a little while to launch. Let me try it with Redis CLI. Auth. Helps if you type password. Very secure password there. Get foo. Redis is loading. Yeah. Yeah, I need to. There we go. There we go. So Redis is happy now. Just maximize that and get him out of the way. There we go. And then I'm going to put this to the left, this to the right. We don't need that. So I'll go ahead and launch the web server. And then we'll look at the code some more. The more interesting thing here is build.py. Build.py is the thing that builds the data, populates the top K thing. And so I've got this data set here of these UFO sightings. It's a CSV file. It's all 112,000 of them. Yeah, I know. And so you can see that there's quite a bit here, right? Man and woman observed cluster of about 8 motionless blinking blue lights, not in sync, right? That is a UFO sighting. Great stuff. USN trained weather observers sighted 3 solid colored lights, 2 red, 1 white. No blue. It's not American or French. And so, you know, there's, if we go down, there's 112,000 and 100 actually. Interesting sites over uptown Minneapolis, Minnesota. Good times, good times. So I have, hang on, written a little Python script here that uses Redis Bloom. I use pandas to parse this really big CSV file. And I'm using NLTK to tokenize the descriptions of the UFO sightings and to import a bunch of stop words, because I don't want the top 10 most commonly used UFO words in UFO sightings to be a, and, the, is, are, of, that kind of stuff. I want it to be actually interesting words. So I pull in the stop words, and then here I'm just, I got a little main function. The key thing here is that I create my Redis clients. I get rid of my 2 fields just in case they're there from a previous run. And I am calling top K reserve. And so here's that width, that depth, that decay. I want the top 10 items for words and shapes. Here is, and this is why you always turn off notifications when you're giving a presentation. I'm sure you all heard the loud ping, right? Yeah. So we read in that CSV file. We're using pandas here to get just the columns we care about. And so we just want the text and the shape. We don't care about any of the other data. And then we want to make sure they're all strings so that it doesn't interpolate empty string into NA and stuff like that. And we return that data frame. And then here we process and we just loop over that data and get the shape and the text. And text parses the words out. Parse words just calls tokenize, which is part of NLTK. And then we've got a comprehension here to do that, where we get all the words if they're not in stop words and they're alphanumeric. So, because the tokenize will put like periods and stuff like that in there as well. So we get our words, we get our shape, and then we call topk.add, passing in the shape, and then we have a little comprehension here to go over all of our words and call topk.add for each word. And so this is not a terribly complicated thing. I think the hardest part of this was setting up, was probably working with pandas, honestly. So, but that's the code we have here. And there's a little bit of JavaScript code to put this on a screen. And so I'm going to go ahead and bring up a browser. I probably have one already. Localhost, is it on 4,000? Nope. 8,000? No, I could just look. 5,000. I knew I'd get there eventually. And I know you guys aren't seeing that yet because I haven't drug it up there. But okay, so here's my little app. These aren't doing anything yet. There's just nothing. There's no keys in Redis for it to query. There's no nothing going on. So this is going out there, and oh yeah, I added authentication. We're gonna change the code here on the fly. No, what we're gonna do is we're gonna turn authentication off on Redis. By default, protect mode is enabled. I think, oops, that'll do it. And then we'll wait for it to load up the AOF file, which I need to pare down. It's taking too long for my Redis to start up. Sorry, I'm running a little long here. I should have rehearsed my demo like a professional, but here we are. Still loading.
So, Guy, are we going to be? Is this demo going to be posted online for people to run after the meetup?
Yeah, it's actually out on GitHub already. So,
all right.
I will share the link to it here.
Does it have all its dependencies, or
you'll need to launch Redis?
All right.
So you'll need to install your own Redis.
Okay, but it would tell whoever clones the thing what they need to do to set up a Redis account and stuff.
I think so. I may not have added that much to it yet, but let me paste that into the chat.
A reminder.
There we go. That's this has this and the slides. Actually, I don't think it has the slides, but it has a link to the slides. So it's complaining here that the key doesn't exist. That's correct, right? The key doesn't exist. If we go ahead and over here now run build.py, it's going to start adding keys. Now it's going through and it's adding all these words. And we can see now in real time, this is updating periodically. It's showing me top UFO shapes and the top UFO words. And I'm pulling that count out of the top K, although it's probably larger than that. Light and lights are popular, are the top two right now. Objects there. Sky is a popular word, which these all make sense if you think about the nature of UFO sighting, right? But yeah, and you can see it's actually going fairly fast. It could be a lot more performant than this, but I wasn't targeting towards performance. I was trying to get it to be visible. And so like I'm printing out and parsing the file constantly, and that's all very slow. You could make something that was a lot faster than this. Redis should be able to tear through all this data in a couple seconds, but I'm doing it in such a way that it can't, because I'm basically loading it all in Pandas, and then Pandas is doing all this stuff, and so there's other bottlenecks. But yeah, so this is some Python code that I wrote that used Redis top K, yeah, I think top K is kind of cool. Doesn't take up a ton of space, which is the big advantage of the probabilistic data structures in general. They tend to be nice and fast, and they tend to but you get that speed and that space savings as a trade-off of accuracy. It's not completely accurate. So let's see. Yeah, let's bring my slides back up. Just let that run in the background. Okay, so here's some links that are useful. The bloom filters by example is where I learned how bloom filters worked, how they worked. There's a really great example on there. The bloom filter calculator I mentioned earlier. Min-hash tutorial talks about how min-hash works. This is a white paper on how HeavyKeeper works. It was very dense and hard to read, but I was able to figure out how the algorithm worked based on it. If you want to play around with this UFO data set, you can go out to data.world. Timothy Renner created this. He's the same guy that created the Bigfoot data set that I like to use. Here's the National UFO Reporting Center, because I mean, who doesn't want to go there? Redis Bloom, if you want to download Redis Bloom and play with it with your Redis install. And then here's a really good blog post on how Top K works within Redis. So that's pretty much all I got. This is the link to the repo that I just pasted out in the chat. These slides are available, but they go to Showpad, which is sort of like SlideShare, but then we get analytics. But you should be able to just access them. If you can't, email me, let me know, and I'll see if I can figure out why they're not accessible. So, and if anyone wants a copy of the slides, I'll just email them to you. So, yeah, that's pretty much all I got. Are there any follow-on questions? Or any questions, I guess, at all?
Did you find out whether or not aliens or Bigfoot was flying the UFOs?
I believe the UFOs act as sort of like an Uber service for Bigfoots, or for the big feet. I think that's how that works.
You didn't find a correlation like Bigfoot sightings always happen where UFO sightings happen?
I
Almost
actually
like the same people.
yeah, I actually tried to map that out when I was looking at the data set. And for the most part, you had a huge spike of UFO sightings back in the 50s, because that was like the heyday of UFO sightings. But Bigfoot sightings weren't that big. Bigfoot sightings started creeping up in the 70s and then dropped by the time the 80s started. And then both UFO and Bigfoot sightings started increasing in the mid-90s when the internet started taking off, which I think is very telling. The Bigfoot sightings dropped off after a while, but the UFO sightings continued on with ever increasing frequency. So I actually did look at that to see what those numbers looked like, and there wasn't really a strong correlation. I think the increase in the 70s was a result of the $6 Million Man.
Oh. The day the Earth stood still was 60 something.
Was that early 60s, or was that in the 50s?
It was still black and white, and it was at least 1960.
Yeah, but that was like the peak of UFOs. Everyone was, after World War II, and it probably the guy who gathered this data actually has a great thing where he observes that most UFO sightings are within 50 kilometers of air bases, like Air Force bases. And the most common day of all the days in the calendar for UFO sightings is July 4th. What is that in the sky? It's definitely a UFO. It couldn't be fireworks. So, this data is actually really fun to look at and find other patterns in. I used it quite a bit when I was at Data Robot doing AI stuff as well. So
on July 4th, there'll be military jets doing flyovers over parades and that kind of stuff.
Yeah.
And folks might be catching those just in between.
Yeah. The actually, I may bring it up to share. If you go out to the guy's site, he blogged about it. It's like dramatically taller. Like they're all down here, and there's one that's 10 times taller than the rest of them, and that's the 4th of July. The next biggest day is New Year's Eve. So
I wonder if alcohol's involved.
I'd be actually one of the people, if you got to Data World, took the Bigfoot sighting data and mixed it with drug and alcohol use data to try and find correlations. My theory, looking at all this data and just plotting it out over time, is that it's their cultural phenomena. I mean, my memory of the 70s and the idea that Bigfoot, it kind of aligns. You know what I mean? If you think about remember In Search Of with Leonard Nimoy and and all that stuff. It was just sort of Bigfoot was a popular idea in the 70s, and then it winded down into the 80s. The UFOs were a popular idea thanks to the X-Files, and so maybe that's what pushed the UFO sightings up. But I think it's mostly a cultural phenomenon. So, any other questions?
Yeah.
Cool.
I
Thank you, then. Thank you very much.
for coming out and joining,
Thanks a lot.
for sharing. And there was some Python at the end, so all is good.
Yeah. Well, and the data structures themselves are just sort of a universal computer science thing, and so I feel like they're applicable to anything you're using. I mean, you can implement these probabilistic data structures in Python.
Yeah. And well, thanks for joining us and for giving the talk.
Yeah, absolutely.
And
Yeah.
we'll probably have to do something similar for the next talk in April.
Yep.
I doubt the libraries will open up again.
Yeah.
Right.
Yeah, and we've got links posted in the chat so that everyone can see what's going on with the slides and the code that was given. We've got links to the actual mailing list for CohPy so that you can see or hear about anything else that comes on. If I can remember, I'll post some notes from the dojos for those of you who aren't able to make it.
Cool. Well, please post those links in the chat channel to the mailing list
Yes,
so they don't get lost.
right. And the next
URL for the recording.
Oh, yeah, hang on.